So we ended the previous recording with nice theorems. This recording, we're going to continue with nice theorems, so to say. Pratt error results for uniform sources. So now we're going to compare only uniform sources. And here's a theorem. So I'm assuming all the sources now are uniform. Then we have source preference for C over A, if and only if the source function of A results from the source function of C by composing with a disliked function phi. So disliked means it has sort of source preference over expect utility, the absolute condition. So if and only if. So this is quite the Pratt arrow spirit. You have the same for insensitivity, more insensitive for A than for C, if and only if the source function of A is the source function of C composed with the insensitive phi function, the transformation function. And we have a third theorem of that kind that quite reinforced our self-confidence. We have both equal sources A and C. They're equally good regarding source preference, and they're equally good regarding source insensitivity. That holds if and only if they have the same source function. So they have completely the same uncertainty attitude. Now this theorem, quite as I said already, it was quite helpful to us. This gives the feeling that completely, if you have source preference and source insensitivity, then you completely capture the uncertainty attitude, the ambiguity attitude. If two sources are the same on those two components, then they are completely identical concerning their uncertainty attitude. So it gives a sort of a feeling, well, that we have the right definition. They capture the two components of uncertainty ambiguity. So that's reassuring to us. But also it shows you need both of these to get identical source functions. Almost everybody in the literature, for instance, we can apply this to the special case of ambiguity. We have, this is the case where source C is your ambiguity is simply how much an uncertain source differs from known probabilities. So here, if for source C, we take the risky source, then we see this theorem shows how the source A deviates from the risky source, so the ambiguity attitude of the source. That's roughly what you capture here. But then many papers in the literature, they define ambiguity neutrality as only that you have no source preference for risk over the ambiguous source or the other way around, that they are equally preferred, equally liked in terms of that preference component and the inequality of weights given anyway. So that's what almost everybody in the literature does. They then completely ignore the insensitivity component. I think it gives the wrong concept. They, indeed, the two source functions are equally liked, but they are not identical. For instance, this may be a bit vague for people, but let me give a concrete example. Imagine that a decision maker for objective probabilities for risk is just doing expected utility maximization. So this double probability transformation function, the source function for risk, is just the identity, linear function, the identity. But assume that this person is also facing an ambiguous source, maybe has a sort of continuous distributed known earned composition and also unknown. And for the ambiguous source of uncertainty, the person have a strongly inverse S-shaped source function, but it is symmetric at 0.5, value 0.5 at 0.5, but for probability 0.5, but other than that, it's strongly inverse S-shaped. By almost all the definition in the literature, such a decision maker is qualified as ambiguity neutral because he has no preference, source preference for the ambiguous source over risk or the other way around. He likes them equally much. In a way, you can say that. But still, this person, you can call that person ambiguity indifferent. I think that's a good term. But this person is very much reacting to ambiguity, very insensitive for the ambiguous source and not at all for the objective source. So you can't say it's not the same ambiguity. It's not ambiguity neutral, that person. So therefore, this theorem shows that we get the component, but you need those two components. If you ignore insensitivity, you're missing many relevant things empirically already. I told you empirical evidence showed there's a lot of insensitivity, but also conceptually, this result shows you mathematically, conceptually. If you do not incorporate insensitivity, you don't capture everything of uncertainty and ambiguity. So I admitted that this insensitivity definition that we have is quite difficult, but you have to work with it, solve it, not ignore it. And this theorem quite helped us to think that way. Now here, this phi function, it's always the same sort of formula. It's quite interesting, that function that captures the comparison between the sources. So we call it the p-matcher. And I'll tell you in words, you can see the algebra, you just take my word for it, what it is. The p-matcher, what you do, first you take a probability of one source, then you take the gambling equivalent probability of the other source, and the function that maps the probability from one source to the gambling equivalent probability for the other source, that is called the p-matcher. That function is really interesting. That function shows you what is the difference between the two sources regarding ambiguity, uncertainty, attitude. For instance, let me, to further your understanding, let me take the case where capital C, the source, is risk. In that case, for instance, imagine that you have two continuously distributed earn with known composition, known probability, earn with unknown composition. And imagine that for the probability, for a subjective a neutral probability 0.5 of the ambiguous earn, gambling on that is equivalent to you to gambling with an objective probability 0.4. So then this p-matcher matches the ambiguous 0.5 probability into the unambiguous 0.4 probability. So that is capturing the attitude, ambiguity attitude. And that function has been known before. There's a paper by Dilma Kouwenberg and myself in Management Science 2016 calling that matching probability. So matching probability is a special case of p-matcher where one of the two sources is risk, is objective probability. And p-matcher then shows you how to generalize this to general sources of uncertainty. So these theorems show this p-matcher, well, you need to know the subjective those a neutral probabilities, and you have to measure them. But once you have them, you can very easily get the p-matcher, and then you know what the difference in attitudes between these sources is. So this shows you, preference axiomatizations. One useful purpose is to make normatively more convincing, or maybe normatively criticized. You can also use them for that model. Another useful purpose is it shows you what the critical empirical condition is that you should test empirically if you want to verify or falsify a model. But a third use of preference axiomatization, they can show you what the right concepts are, what are the things that you should try to measure. Here, these axiomatizations, they show you that the p-matcher, that's the thing you should try to measure empirically if you want to compare two different sources. Find the gambling equivalent probabilities of one source, how they are related to gambling equivalent probabilities of the other source. Then you know the difference in attitude. And for ambiguity, then you know what the ambiguity attitude is. So in that sense, these theorems are nice and useful. And one more thing I want to say is I told you these are Pratt-Arrow type results. Maybe you remember Pratt-Arrow for decision maker and risk with respect to utility. One decision maker is more risk averse than the other, if and only if his utility function or utility function is a concave transformation of the function or utility function of the other. But then a mathematical difference, those transformations are always inserted to the left of the functions. Our transformations are inserted to the right of the functions. They are mathematically different in that regard. And it is because we are not doing within stimuli between subject comparison, but we're doing within subject between stimuli comparison. We're doing a bit of a different thing. And it's also mathematics. So we need different kind of proofs. So in that sense, the mathematics that we have here are different than Pratt-Arrow. We also show here that if you want to analyze probability weighting function for uncertainty attitudes, you need a little bit different mathematics than Pratt-Arrow. You have to put the transformation to the right of functions, not to the left. And we don't. The preference axiomatization show it to us. We just prove it. Now I go on to tractability of our theory, and many people complain. For instance, special case of rank-dependent utility experience. People often complain that the formulas are difficult. But I really disagree. The formulas are easier than for other models. Let's give you an illustration of it. First, I write the formula for classical expected utility for a uniform source. And we notice this is one way to calculate expected utility. Let me explain what's happening here. the act, X, I denote X, that's the act. Now, for this is the savage subjective expected utility. So we have a subjective probability distribution over the state space. So for the act, we can determine the probability distribution that it generates over the outcomes. Then we can also get the probability distribution that it generates over the utilities of outcomes. Now, what I wrote here, this capital G of X and U, is the distribution function of the probability distribution generated over the utilities. Well, it's a dual, it's one minus that, but okay. And it's well known, one of the many ways to calculate integral expectation is to integrate. By the way, I'm only assuming positive outcomes today and positive utilities. No, let's not get negative. Anyway, so then just integrating that function, that's one of the many ways to get the expected utility. It's very well known, every probability theory textbook shows it. So now, if we do this, so I told you all the theorems are valid under biseparable utility, but now I'll look at the special case of rank-dependent utility, Schucker expected utility, which is maybe the most important case, I think, of biseparable. But anyway, here the formula looks like this. It's just like the one above, only that the dual of the distribution function should be transformed by means of the source function. That's the only thing. So you do just the kind of calculations as you do a classical Bayesian, only you add one, you composition, you add one transformation. That's not very difficult computationally or conceptually or whatever. It's quite straightforward. Of course, if you want to do this, you have to get the distribution or the dual of the distribution. That may not always be very easy, but there are other formulas of rank-dependent utility or Schucker expected utility that ask you first to rank the outcomes and then do some calculation. Many people complain, oh, you have to rank outcomes, that's difficult. I think, come on. For instance, in the multiple prior models, for just to evaluate one X, you have to solve an optimization problem over a set of probabilities. That's way more difficult than ranking a few outcomes. And in the smooth model, you have to carry out, just for the evaluation of an act, you have to carry out an extra integration. That's also way more difficult than ranking outcomes. So I think Schucker expected rank-dependent utility are computationally tractable and easy. And here this formula shows it in particular. Now, something else about tractability. If you want to, for instance, imagine you are interested, let's, the special case where C is risk and A is an ambiguous source. And you want to write C, how the ambiguity of this A is changing the formula that you would use for risk. What you do, you get this formula. You get, what you do is here you can use the source function for risk, for the probability transformation function. And then here you put the P matcher from A to C. So this is these two together are the source function, the theorems on the previous slide loaded are the source function for ambiguity. So ambiguity, bringing in ambiguity is simply bringing in this transformation. If you dislike ambiguity, you have ambiguity aversion, you put here a function that is disliked, that pushes the weight down. If you are in, maybe it's not so much like or this, but you say, I feel extra uncertainty about the ambiguous. These are ambiguous probability. They feel vaguer, more uncertain than regular probability, than objective probabilities. So that means that I should reckon more with deviation from the expectation than if it was objective probability. If you have that attitude, you want to increase the uncertainty, that's like increasing variance, moving mass to the tails. That is simply taking an insensitive, so an inverse S-shaped transformation function, because that inverse S-shape is simply moving mass to the extremes, like increasing variance. It's an expression of increased uncertainty. So that's also very easy to do. If you want to use, or if you want to policy, maybe for I'm a Bayesian, but if non-Bayesians want to apply these theories prescriptively and with a policy make on climate change and so on, they can just tell you, okay, you feel uncertain about these probabilities. You can bring it in by putting there an inverse S-shaped transformation function to any extent that you want. So this is very tractable, easy, conceptual. Continuing on the tractability, a very big advantage of the source, the theory that I'm presenting today that I didn't say anything about yet, is coming now. And that is, here is a graph. This was already 2011. I told you already, the source method has already been used in many empirical papers. But we justified axiomatically to do this. But this was in 2011 using the source method. Here was one subject in the experiment measuring the source functions for many sources of uncertainty. And the big pro of source function, they are graphs, functions from 0, 1 to 0, 1. You can show them visually as a graph. So here we have, for instance, this is the source function for risk. So that's the regular objective probability transformation function. This is the source function for Paris temperature. And you see Paris temperature is more insensitive than risk, but it's not more disliked. It's almost liked almost equally much. So, and here you see the source function of foreign temperature. You see that this disliked much. It's completely disliked more than Paris temperature. So immediately visually you can see what's going on. So that's a very big pro of this new theory. And also for non-Bayesians who want to use this for policymakers, you can even not write formula. You can just sit down, to draw the graph, maybe draw the transformation function for objective probability. You say, now you feel that the probabilities that you have for climate change are vaguer, right? So we must reckon more with uncertainty. So then let's move a bit of mass to the extremes. Is this how much you want, how you feel? You can just, you can work with policymakers. Not even you need formulas. You can use graphs to visually see what you're doing. I think that's a very big pro of this new theory. So I'm claiming much tractability and convenience. There has been in 2014, there has been a book called John Hay and some co-authors, Maffiati and I forgot. Anyway, there was a horse race for ambiguity theories. And then the paper here showed that the source method would be the winner of that. So in a prediction competition between several ambiguity theory, the source method was doing best. But that's another illustration that is a good theory, work well. Convenient indexes have been provided. If you want one numerical estimation index of how insensitive a person is, or how much the person dislikes ambiguity, whatever, those indexes have been provided with all kind of theoretical justifications. So many now maybe discussion, I'm going to let me skip. I don't want to speak, hope that my total speaking time is within an hour. So the discussion section is mentioning all kind of desirable features that we have, but maybe you can stop the video and read them if you like. I don't want to spend much more time talking. I said all these things already. It's summarized here. Many new insights come from it. For instance, that P matches other functions to measure, to compare sources of uncertainty very conveniently, all kind of other insights that you should not ignore. Insensitivity if you want to define ambiguity and neutrality. But I said all these things. People can stop the video, read. I want to go to the conclusion, not to spend too much time talking. So conclusion, first of all these concepts that we defined and introduced, resulting from long, hard work, they are all fit together in natural ways, supporting our belief that we have that we defined the right concept of ambiguity, and we did it in the framework of Savage, which is more pure and to the point, I think. Further, so it is possible to the Savage. I put here also Gilboa, because Savage framework, it was really Gilboa who gave the axiomatization for ambiguity theory. It was a great contribution. So we're building much on his 87 paper. And then I promised in the beginning, we show you how to use probability weighting function to study uncertainty. And I hope that my promise has been fulfilled. Then here is where I am concluding the lecture.